Hello everyone, welcome back. So let us continue our discussion. We are in lecture 4 of week 8. Now in the previous lecture, we defined shear center, right? If you recall, we derived the expression of shear center for a channel section. So if you have a channel section like this, which is subjected to bending, then and the shear force is V at this particular section. So if we apply the shear force, which is at a distance E from the vertical axis of the wave, so this is the shear force, then this point, which is at a distance E, is the shear center. Now the expression for this E we derived, and it was B square D square T divided by 4I. And also in the previous lecture, we derived the expression for sigma x if the section is having arbitrary cross section, and for that the expression is y times Iy minus z times Iyz divided by Iyz square minus Iy Iz times the moment here. And also we derived the expression for tan beta, which is equal to Iy divided by Iyz. So for any arbitrary section, then we can find out the orientation of the neutral axis from this beta, and then we also get the bending stress distribution. And if we have a channel section, for that we derived the location of the shear center, which is having a eccentricity of E, and this is the expression. Now today we are going to investigate if we have any arbitrary, say, shape of a channel section. Say this is the shape of the channel section whose thickness is T, and for such a section, what is the location of the shear center? We can intuitively think that it will be somewhere here, and through this point we have to actually apply the shear force V. So this distance from some reference axis, we have to define that distance is the location of the shear center for this particular section. So we'll investigate this in today's lecture. Now for that, again, let us draw the section of the beam. And if you recall, what we did is we considered two sections at a distance dx, and for them we identified unbalanced force, and that unbalanced force actually gives the shear stress distribution, right? So let us follow the same path, but before that let us draw the 3D view of this section. So this is a part of a beam, so that is the beam section, and for this section again we apply bending moments at the ends, and that will be of magnitude say m, and this face we have m plus dm. Okay. Now obviously because of that it will at the section level it will develop shear stress, because this bending will cause unbalanced force, which will be balanced by the shear stress developed at the section. So for that what we do, we consider a section which is at a distance, say this section of, so this curved path is ds, so that is ds, and then what we'll do, we will identify the unbalanced force over this small section, and for that again let us consider the shear stress flow. So if you see, this is the cross section. Now at the section level the shear flow will go like this, and here obviously we'll have in the opposite direction, and that's how the shear flow will occur. Right. Okay. Now let us find out summation of all forces Fx is equal to 0. So this direction is x. Now over this cross section ds, so at this face here the stress is sigma x plus its derivative with respect to x, and which acts over dx. So that is the total stress multiplied by T times ds is basically the total force. So what we have to do, we have to integrate from 0 to s over full curve length. Now this is over the right face, then this minus, again on the left face we have sigma x, then T times ds, and integrated over 0 to s. Now this shear stress, say tau, and it is acting over x plane and along s, so we call it tau xs, and obviously this shear stress we call it tau sx. Obviously tau sx equal to tau xs, that we already know. Now there will be the shear stress, that is this one, tau sx times T is the thickness and it is acting over dx, which is equal to 0. So this is the balancing force which is actually balancing this unbalanced force. So what we get effectively for this arbitrary cross section is tau sx is equal to minus 1 by t integral 0 to s differential of sigma x with respect to x times t times ds. Actually, we can replace this delta with d. So this is the length of the cross section. Okay. Now this t will get cancelled. So what effectively we have is minus 0 to s dou sigma x dou x times ds. Now let us recall the expression of sigma x for any arbitrary cross section. Sigma x equal to y I of y minus z I of yz divided by iyz square minus y iz times mz. Therefore, if we differentiate both sides with respect to x, what we get is obviously y times iy minus z times iyz divided by iyz square minus iy iz times differential of mz with respect to x. So we know this is equal to the shear force acting at that particular section. Now what we get is tau xs or tau sx is equal to minus 1 by t 0 to s differential of sigma x with respect to x times t times ds. Now in place of this quantity we can use this expression. So what effectively we have minus 1 by t 0 to s, we have y I y minus z I yz divided by iyz square minus iy times we have t times x. And in place of differential of mz with respect to x, we have shear force V. Now, if you further solve this expression and simplify, what we get is V divided by T and 1 by Iyz square minus Iyz. Then we have integral 0 to s y of Iy minus z of Iyz times t times ds. So we can further simplify this expression, minus v by t, then we have 1 by Iyz square minus Iy Iz, and then we can open this bracket, so we have Iy 0 to s yt times ds minus Iyz integral 0 to s zt times ds. Now if you recall, for rectangular cross section, what is this expression? It was q, but this time it is q because we consider y, that means this is qz and this is qy. So we get the expression of shear stress distribution tau Sx is equal to minus V, then we have Iy times Qz minus Iyz times Qy divided by, we have Iyz square minus Iy Iz times T. Obviously, tau Sx equal to Xs. So we get the shear stress distribution over an arbitrary section. Now, as a special case, if we put Iyz equal to 0, that is the section is symmetric, then we have tau Sx is equal to minus V, then within bracket we'll have Iyz 0, so we'll have Iy times Qz divided by minus of Iy Iz times T. Then this Iy gets cancelled, so we have Vq by Iz T, which is the expression we derived earlier, Vq by Ib. Okay, this is the expression. Thickness T here was actually B for the rectangular cross section. So this is the same expression we get again from this general case, where now we have the expression for shear stress or shear flow over the cross section, which is having arbitrary cross section, and for that arbitrary cross section we know Iy, Iz and Iyz. So once we know these three quantities, then we can actually evaluate the shear stress at any particular section, and then just by varying the location we can plot the shear flow, right? Now let us now investigate what should be this eccentricity E. Now for that, again, V times E is basically the moment, and that should be equal to the moment of tau Xs or about the point 0. So if we see the diagram, in this diagram we have the center point. So with respect to that point, we actually quantify the location of the shear center. So if this say somewhere here, that is the O. So from this point, we define this eccentricity, and actually this direction we have Z axis, and this direction we have Y axis. It's actually not here. Let me redraw. Just this will be here. So that is the Z axis. And here is the shear center. And that shear center having eccentricity E. So for this third path, we have already quantified the force Fx, and from this center of this force, we know the distance. This we can quantify. So that distance will give us how much moment is caused by the force over this cross section, and if we integrate over the entire length, third path, then we'll get the moment, which will be balanced by the moment V. V is the shear force at that particular section, and E is the eccentricity. So effectively what we'll get, E is equal to this moment of tau Xs about O divided by V. So we get the location of the shear center for any arbitrary cross section. Now let us take a quick example. And with that, we'll close our discussion on shear center. Let us continue with a different problem, and this time we have a circular cross section but not completely closed. It has a opening. You can see here a small cut here, and for this section our aim is to find out the location of the shear center, and for that first we have to identify the shear flow over this cross section. Now, first thing, if you recall the expression we derived, tau x s is equal to minus v times iy qz minus iyz times qy divided by iy z square minus iy iz times t. Right. This is a generic expression and true for any arbitrary section. And where from it comes again, if you recall that we first identify the unbalanced force, and that is balanced by the shear stress developed at the section level, and that's how we derive this expression, right? Okay. Now, the thickness of this beam is, say, T, and the radius is R, right? So what we do, we first consider small wedge and say this is d of phi, and another section at an angle theta. So our task is to find out the amount of shear stress developed. You can see the dotted line which is passing through the middle of the section, and the direction is like this. So our job is to find out the value of the tau sx, right? That we'll do in a minute. And for that, we consider a curved path. So this is, say, ds, and the thickness is t. Now, we can find out what is q. Q for this case is r d theta, d phi times t is basically the area of this small wedge that we consider, and we have to multiply it with the CG of this section with respect to our reference axis. So the lever arm in this case is r sine of phi, right? Now, to find out q, we have to integrate it from 0 to theta, right? Because we'll find out up to this theta, if we consider here, then what is the amount of shear stress developed, right? Okay, so if you complete this integration, what you get is r square t times 1 minus cos of theta. Now, once we find out q, if you recall, we can find out tau. Tau is nothing but vq by ib, right? So for our problem, we have shear force at the section level is V. Q we have already derived, that is r square t times 1 minus cos of theta divided by, we have I, and for this circular section we can evaluate that, that is pi r cube t times we have another t. Okay, So the expression for tau, what we get for this section is V, then R square T will get cancelled. So we have times V times 1 minus cos theta divided by pi r T, right? So that is the variation of shear stress at the section level for the circular section with a opening here, small opening. Now from this expression, what you can see is as we change theta, the shear stress distribution also changes over the entire cross section. So for theta equal to 0, obviously cos theta is 1. So we'll have tau equal to 0. So for theta equal to 0, tau is equal to 0. Now, when theta equal to 90 degree, that means we are here, then tau is V by pi RT, right? And when theta equal to 180 degree, that means we are here, then tau is equal to, we have 1 minus cos theta, so that is 2V divided by pi RT, right? So that is the shear stress distribution. Now we can also find out the moment, and that moment, if we estimate, we have tau is the shear stress at the section level, and it is acting over a small wedge, and its area is, say, R d phi times T. So that's the amount of force times the lever arm is R. And then we integrate it between 0 to 2 pi. So we can put the expression of tau here that we have already derived. So expression of tau is here. And if you complete this integral, so what you will get is 2V times R. So I leave this as an exercise for you. So what you do, in place of tau, you put the expression that we have already derived here and then complete this integral. So for an angle, say phi, if this is phi, so in place of theta you have to put phi and then put it back here in place of tau and then complete this integral, right? So what we get is the moment caused by this shear flow is twice VR. Now recall, we have shear center somewhere here, right, over the horizontal axis, right? Now V times E, that is the location of the shear center from the origin, is equal to the moment developed, so that is twice VR. So which indicates E, that is the location of the shear center for this circular section with a small cut, is twice R, right? So E is equal to twice R, right? So that's the final outcome. So if we have a circular cross section with a small cut, that is important, because if it is a completely circular cross section, then it is symmetric about Y and Z axis with the origin here, and therefore shear center is also here. But the moment we introduce a small cut here, you can notice that the shear center is at a distance E, right? And the expression of E is twice of R. R is the radius of this circular cross section. Now if we plot this diagram, so what we get is at theta equal to 0 or close to 0 here, we have tau equal to 0, that we have already derived. So tau is 0 here, right? Now at 90 degree, so we are somewhere here, is the theta equal to V by pi R T. And when we are here at theta equal to 180 degree, we have V by twice V by pi RT. So that's the shear stress distribution over the entire cross section for this circular section with a small opening, right? So now you can see how you can use the theory that we have developed to first find out the unbalanced force, and from the unbalanced force you can actually find out the location of the shear center for any arbitrary section. Okay, I hope the theory is clear to you. So try to solve some problem, and then if you have any difficulty you can raise your question through emails or during the open session. Thank you very much.